Okay, so I will continue the previous lecture. So in this section, we defined the Henkel determinant, and we defined a bunch of things and proved several things. And a nice thing about the orthogonal polynomials is that there's a simple criterion like this. For a linear functional with moment sequence mu n, this is an orthogonal there is an orthogonal polynomial sequence for this linear functional if and only if the Henkel determinant is non-zero. And so we prove this, and when we have a monic orthogonal polynomials, then we know how to compute is squared applied to this linear functional in terms of Henkel determinants like this. And we also can write down the monic orthogonal polynomials explicitly using the determinant, Henkel-like determinant, where the last row has x's in it. And we define this notion of a positive definite, and a linear functional is positive definite if this holds. So if the linear functional of applied to some polynomial satisfying this greater than 0. Okay, that was the definition of the positive definite. And we showed the last class that if L is positive definite, then there's a real orthogonal polynomial sequence for this linear functional. That's what we showed last time, right? And because this condition is, let me give you a name to this. It's not, because it's kind of long to say this all the time. So let me briefly define that. A polynomial is, let's say, a polynomial pi of x is non-negative valued. So the name really explains it all, right? If pi x is non-negative for all real number x. So non-negative value. So real valued polynomial is basically polynomial whose value is real for every x. So this means L is positive definite. Using this definition, L of pi of x is positive for all, maybe I can, non-zero, it must be non-zero, like non-zero, non-negative valued polynomial pi. Okay? That's I just rephrase the definition. And what I'm going to tell you now is that y is called positive definite in this case. Because positive definite is a commonly used term in linear algebra. So, but so far we don't see any connection, and there is a very close relation between this and the notion of positive definiteness in linear algebra. So we will see the connection. But before that, let me prove a simple lemma about a non-negative valued polynomial. So suppose that let pi be a non-negative valued polynomial. Okay? Then it has a nice expression like this: p of x squared plus q of x squared for some real polynomials px, qx. Okay. So we will prove this. this a little bit. So proof of this theorem or lemma. First, we will show that actually real valued polynomial is always a real polynomial. So since pi x is real for every real number, non-negative value, that means is real automatically, right? It's real and also non-negative. That's what non-negative means. So since this pi x is a real polynomial, if you want, you can prove it by considering the leading coefficient. So if you want, because leading coefficient of what is the leading coefficient of pi is if the degree is n, you divide this by x to the n, and you take the limit x approaches infinity, is going to be the leading term, right? Because only the leading term survives. So you can get the leading coefficient, but this is, of course, real because real valued. So this is going to be a real number. So the leading coefficient is real, so you can get rid of the leading coefficient, and you can repeat this, then you get that all the coefficients are real. So real polynomial is just almost immediate. So now we have a real polynomial, okay, a non-negative value for every real number. Then just imagine the graph of the function y equals pi of x. Now just imagine since pi x is greater than or equal to 0 for all x. If you imagine the graph of this y equals pi of x, all zeros or roots, they mean basically the same, all roots of pi x, okay, all real roots, have even, even multiplicity, right? Because you can factor this out. Otherwise, if you write the graph y equals pi of x, if it has odd, 0 means it touches the x-axis. If the multiplicity is odd, then it looks something like this or something like that. So it will always have negative values. So that's why it's non-negative values. And that means it may also have complex roots, right? The complex roots will always come in pairs, conjugate pairs, because it's a real polynomial after all. So, and its complex roots appear in conjugate pairs. So that means we can write down this. If you consider the factorization of pi of x, then it will be something like, okay, let me write this way, r of x squared for real polynomial r. And for complex roots, we can write, maybe I should not write I here, k equals 1 to n, x minus alpha k minus beta k j. If this is minus of this is the root, then it's ki. Its complex conjugate must also appear. Okay. Of course, all the r of x is the real polynomial. Alpha k, beta k are real numbers. Then this, if we write, so we'll just let's write this This is a complex polynomial. So we can write this as a real polynomial plus I times another real polynomial like this. Okay, so AB are real. AB real polynomial. Then if you take the conjugate, taking the conjugate, you get conjugate is multiplicative, so we get this. Then just substitute it all there, then we get AX plus IBX, AX minus IBX, which is RX, AX squared, BX squared. So if you expand it, yeah, P squared and then Q squared. So that's the proof. So because of this, so now let's look at this definition again. L is positive definite if and only if this is positive, if this is non-negative valued polynomial. But non-negative valued polynomial can always be written in this way. So it's enough to consider px squared there for a non-zero polynomial p. So this means, therefore, by the lemma, L is positive definite if and only if, maybe I can write this way, if and only if L of px positive for any non-zero polynomial, sorry, that's scared, non-zero polynomial px, right? So this is the an equivalent condition for this. Okay, now the question is why L is called positive definite. And recall an n by n matrix, a square matrix is, let's say, let's focus on the real, a real n by n matrix is called positive definite if a matrix A is called positive definite if U transpose A U is positive for any non-zero vector R to the n, non-zero vector. Okay, this is the definition of a positive definite, the usual definition in a linear algebra. And there is a criterion called the Sylvester's criterion. This criterion says that A is positive definite if and only if every principal minor of A is positive. Here, principal minor means, I guess most of you already know this, but principal minor means if you have an n by n matrix, you consider any k by k matrix, taking the first k rows and k columns, and take the determinant of this matrix, this submatrix. This determinant of this is a principal minor. Is a principal minor. So every determinant of this is positive, then the matrix is positive definite. That's a theorem due to Sylvester. So now we can justify the terminology positive definiteness. So L is positive definite if and only if. Oh, sorry. I think I already mentioned the real. So this, if it's it's a positive. Positive definite if every minor is this, and every entry is real. So in this theorem, L is positive definite if and only if every mu n, the moment, is real, and this is positive definite. So positive definite also appears here as a matrix. I think this is not very accurate because this is a determinant already. So let me write this way: the Henkel determinant. Sorry about that. Let me write this again. And the Henkel determinant, Henkel matrix. Henkel determinant, delta n is a determinant, so we cannot really use it here. Henkel determinant is exactly the matrix. Henkel matrix is exactly the matrix whose determinant is the Henkel determinant, is positive definite. This is the theorem. Okay. Okay, so let's prove this. For all n. So this direction, positive definite, and this is real, and this is positive definite. But what does this mean? This means basically this means that delta n is positive, right? Because all the minors, all the principal minors of this are already Henkel determinants. Okay, so this really means this. So this is something that we already proved. Let's see. Let's go back. Yes, let's see. Look at this. If L is positive definite, I think I can just copy this. You can see that the Henkel determinant must be positive because of this. So by previous lemma, one of the previous lemma, we have this. Since L is positive definite, this is positive, right? Because this is positive, that means this is positive. But actually, if you 0x, this is just this is monic OPS. This is a positive, which is this is just delta 1, delta 0. This is positive. So the initial condition holds. So delta n and delta n equals is also positive for n greater than or equal to 1. So that's the proof. For one direction is easy. Okay, so the other direction. Suppose that this holds. And we know one of the theorems that we proved in this section is that if the Henkel determinant is non-zero, then there is OPS. So since Henkel determinant is non-zero, because this is positive definite, that means Henkel determinant is positive. There is an OPS, a monic. See the OPS. Okay. So our goal in this direction is to prove that L is positive definite, and we prove that okay, let me just say it's enough to show to prove that a linear function is positive. Because of this, it's enough to show that px squared is positive for any non-zero polynomial px, right? So suppose that this has degree n, then we can write px using the orthogonal polynomial, the monic orthogonal polynomials. Okay, let's say the degree is m, then we can write this way. Okay. Then of course, am is non-zero. The degree is, if the degree is m, the am must be non-zero, right? The top degree. Then let's see what happens. Px squared. Then you just take the square of this and take the linear functional, and by the linearity, maybe I can write I from 1 to m, ai pix, j from 1 to m, aj pjx, and then you take the linear functional there. Maybe I can write right? But then, by the linearity, you can just pull this all outside. And if these two are multiplied, and then if you take the linear functional, they will be 0 unless these two are equal. So you only get those, say I from 1 to m, ai, and j must be equal to I, because otherwise it will be 0. Oh, sorry. Right? But then, what happens? This is non-zero, but actually this is positive. Let's see. Yeah, this is positive because again this. Yeah, by maybe, which is positive. This is positive by star above. These are positive, so this is positive. So these are all positive. So in particular, the I equals m, it must be positive. And these are all non-zero, so non-negative. So eventually it will be a positive. So that's the proof. Yeah. So that's why it's called positive definite. Okay, so that's the end of this section. So we will move on to the next section. Section 2.4. Fundamental recurrence. Fundamental recurrence, also called three-term recurrence. So, this is one of the most important theorems in classical orthogonal polynomials. So, orthogonal polynomials satisfy a very simple and nice recurrence. So, let's say L is an OPS, the linear functional with, let's say, monic OPS. If it's not monic, we can always rescale it to make it a monic, so it's okay. Then these orthogonal polynomials satisfy the three-term recurrence. These satisfy three-term recurrence. Which is there are several ways. Some authors write different way, but I stick to this convention. Pn plus 1 equals x minus bn pn minus lambda n pn minus 1 for some sequences bn. For bn we need index from n from 0, and lambda n we only need index n from 1. With initial condition so p minus 1 it's not needed, so it's going to be 0. We'll just by convention, and p0 it must be 1 because it's a monic orthogonal polynomial, so it's degree 0 polynomial monic is 1 is the only polynomial like that. So 0, 1, and then if you plug in n equals 0, then you can get p1 equals something and p2 equals something. So we can get all the polynomials using this recurrence. With additional condition lambda n non-zero. So lambda n must be non-zero here. This can be anything, but this is non-zero. All right, let's see how we can prove this. Proof. So we already know that these are orthogonal polynomials. So their degrees, Pn has degree n, and the leading term is 1. That's because it's monic. So let's consider the n plus 1 polynomial, n plus first polynomial. So maybe these polynomials are monic. Let's compute Pn plus 1 x minus x times Pnx. Of course, it's a polynomial. The degree is n plus 1. The degree is also n plus 1. But their top degrees are exactly the same because the leading term is 1. So the degree will be less than n plus 1. So at most n. We can write this as a sum over I from 0 to n, ai pix, right? Because the degree is at most n. So we are already quite close to this. I mean, all we need to do, imagine that because we just moved this term to the other side, all we need to show is that we only have two terms here, Pn and Pn plus 1, as Pn minus 1. So Pn minus 2, Pn minus 3, etc. These all have coefficient 0. If you can show that, that's enough. So it's enough to show ai equals 0 if I less than or equal to n minus 2, right? That means we only have Pn minus 1, Pn appearing, but that's exactly this. So how can we prove this? When we have an identity like this, so you want to obtain some information about the coefficient, we already did many times like this. Multiply, if you want to get ai, multiply pi both sides, take the limit linear functional, and use the orthogonality. So let let's say j is from 0 to n minus 1. So take and multiply our common technique, pj, both sides, and take the linear functional. Then what do we get? Here, pj, pn plus 1, let me omit x, and xpj pn equals summation I from 0 to n ai l of pj pi, right? What happens? So on the right hand side, only aj and this survives, because if I is different from j, it will be 0, right? Orthogonality. So we only have one term here, but here, so look at this. They are different because j is at most n minus 1. So this is 0, right? This is also 0 because think about this. Look at this. This is a polynomial whose degree is j minus 1, at most n minus 1. So it cannot be, it's less than the degree of this. So again, by the orthogonality, this is 0. So it's the left-hand side is 0. And this is non-zero. That means aj equals 0. So we prove that they satisfy this three-term recurrence. Okay? But there's one thing remaining. We have to show that this is non-zero. This is not proved here. So it remains to show that lambda n non-zero. So now we have already proved this, so we can now assume this. Our goal is now to prove that an is non-zero. Okay, to do this, again, we will manipulate this identity. This. So we want to get somehow this. So multiply, to do this, multiply x to the n minus 1 to here, the three-term recurrence, and take linear function. Then we get x to the n minus 1, pn minus n plus 1 equals sum x to the n is multiplied, n minus 1 is multiplied, so we get x to the n pn minus bn, x to the n minus 1 pn minus lambda n L of x to the n minus 1 pn minus 1. Okay? And by orthogonality, this is 0. This is 0. This is 0, right? On the other hand, because this is monic, then this is actually L of x and pn equals lambda n L of xn minus 1 pn minus 1. But you know, this is the same thing as p and pn. Why? Pn is a monic polynomial. So imagine that you expand this as xn plus something, something, something. This will all disappear because of the orthogonality. So this is equal to this. And this, of course, equals or this squared. But we proved, what did we prove? Oh no. No, actually, it's enough. This is non-zero. because of the orthogonality again. This is non-zero. That means lambda n is non-zero. Okay, so that's the proof. Okay, everything fine? All right, and we will prove, we will now find some formulas for b's and lambdas. So let me do this in the next page. I'm going to use the same notation, so let me copy this. So we already know this, so we can just say that they satisfy this. Then, what is lambda n? Lambda n is L of Pn squared or L of Pm n minus 1 squared equals delta n minus 2 delta n minus 1 squared, and Bn equals L of x Pn squared over L of Pn squared, and L of P n x squared equals lambda 1 dot 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 lambda n, this, or they're all the same, and delta n is the product of lambdas in this way. One lambda n 1. So if you assume that L of 1 equals 1, then you can just forget about this. So we will often assume that this is 1, so in that case this just disappears. Question? N minus 1? Okay, yeah, thank you. Is that okay? Yeah. So let's prove this. We actually did a lot of work already, so proof is not that difficult. So let's look at the previous proof again. Here, we already proved that this equals this, so lambda n equals this divided by this, right? So this is okay. So we proved this. Right? And also, we also proved L of Pn squared for a monic polynomial. We show that this equals delta n over delta n minus 1, because this lemma, where was it? See, this lemma, okay? So we have basically everything needed. So this will prove this. That's the computation. So let's say 1, 2, 3, or 4. So this means one holds. So what about the second identity? For the second identity, because we want to get this, we will do something over here. So for the second identity, multiply Pn in this case and take L. In the three-term recurrence, say star. Then what happens? L of Pn plus 1 equals L of x pn squared minus bn L of pn squared minus lambda n L of pn minus 1. But many of them, or two of them, are 0. This is 0, this is 0. This is non-zero. This, we don't know. It may 0, it may or may not be 0. But that's not necessary. We don't have to know that. But anyway, from this, we immediately get 2, right? Because this equals this, just divide both sides by this, which is non-zero, you get this. Okay? So it may be 0, bn may be 0, but so this may be 0 or may not be 0. We don't know in general. Okay, so what about the third identity? These are now pretty easy. I guess a third identity is the product of lambdas, and you can get this. This just follows from this, right? And this follows from this if you multiply all of these. So easy from consequence from 1, and this is also an easy consequence of this. So 3 and 4 are just 3 follows from 1, and 4 follows from what? 3. So that's the end of the proof. So we have a nice corollary. If you know this 3-term recurrence coefficient, then you can tell immediately whether the L linear functional is positive definite or not. So suppose L has OPS, okay? Then L is positive definite if and only if, I'm following this notation, Bn real, lambda n positive for all n. Because we know that this is totally, positive definite if and only if what was that? Do I need to prove this? Okay, let's prove this. It's not completely obvious, so let's prove this. So this direction, positive definite, then the OPS, let's say OPS is PX. Monic, we can assume monic. Then Pn, positive definite has real orthogonal polynomials, real, right? So that means we have real polynomials. They satisfy recurrence relation. This recurrence coefficient must be real. So the recurrence coefficient Bn lambda n must be real. You can check this by induction. Okay. So Bn is real, that's done. And it's positive definite. So where is it? By 4 here. We want lambda. So I guess we want 1. Lambda n is positive because this is product of Henkel determinants which are positive because of positive definite. So this is positive. So this is done. What about the other direction? Since okay, Pn lambda n real, Pn is real. Yeah, because the recurrence coefficients are all real, so the polynomials themselves must be real too. And okay, do I want to say? Okay, you know, it's not hard to show. It's easy to see that all moments are real. Why? L of Pn x equals 0, right? For n greater than or equal to 1. So, but this is mu n plus something, something, something in terms of previous moments. These are all real, coefficients are all real, so it must be real. So that's how you prove this. So the polynomials are real, and because of this, 3 by 3 scared is positive. Because this is positive. So is that all? Let me think about it. We also have some theorem. Oh, sorry about that. This is not what we want. Sorry about that. No. Yes, this is delta n is positive. Yes, because these are all positive. So this is positive, but the delta n is positive. That's positive definite. So that's the proof. Yes. Yeah, we are using like a previous theorems or results that we proved already, so we have to go back and forth a little bit, but basically all the arguments are quite elementary. So if you feel this is difficult, then this is because you forgot previous result that we proved. But if you remember all of them, these all follow quite easily. Yeah. Okay. Actually, I forgot to mention one more thing. L of 1 is positive. Let's say L of 1 is positive. Yeah. Because L, if you multiply any constant to L, is still satisfy that, so it's not going to be positive definite, of course. So, yeah, it's positive. All right. So, see, we have three-term recurrences. Three-term recurrence for orthogonal polynomials, but it's only the statement assumes that these are monic. But sometimes, actually, oftentimes, if you look at like literature, especially in like analysis and physics, then orthogonal polynomials they're using are usually not monic. So in that case, if you want recurrence relations like this, you can you have to make these orthogonal polynomials monic by rescaling. But the rescaling is really but just multiplying, dividing the leading term, a leading coefficient of each polynomial. So you can always get monic polynomials and you get a recurrence like this. So let me give you an example. Chebyshev polynomials. We already know that the Chebyshev polynomials Tn x is defined by polynomial satisfying this. This is the definition, and we already know that because we found a measure, it's a linear functional that makes this orthogonal polynomial. So by the theorem, this must satisfy a three-term recurrence. How can we prove this? So it can be done. It can be you can find the three-term recurrence easily because cosine functions satisfy this nice relation to cosine theta cosine n theta. but n must be greater than equal to 1. If n equals 0, this is not true. So that means this is Tn, n plus 1, plus Tn minus 1 equals, this is x, right? So 2x Tn. That means Tn plus 1x equals 2x Tnx minus Tn minus 1x. This is not monic because 2 is multiplied there. So this is n equals 1. But for n equals 0, T1x equals, I think this is x T0, x n equals 1. Because this is 1. T0x is 1. T1x is x. So, right. So how can we get monic orthogonal polynomials? So what is the leading coefficient of this? The leading coefficient Tn x is 2 to the, so you see, if you go, the index is increased by 1, you multiply 2. So it's like 2 to the n, except it starts from this factor appears after 1, so it's going to be n minus 1. Of course, n equals equal to 1. And 1 if n equals 1. Sorry, 0. Okay? That means we can make it normal by defining this t hat to be t and x. We have to divide by this, so 2 to the 1, maybe I can write 2 in front, 2 to the 1 minus n, t and x. If n is greater than 1, and just Tn if n is 0, which is 1 in this case. No, not 1. Less than equal to oh, I think that's right. I think that's right, yeah. If n equals 1, it's the same, but n equals 2, actually n equals 2 is still the same because this is just 1, but yeah. So this is kind of exceptional, but basically we want to make monic. So here, how can you make a recurrence relation for Tn? Then it is Tnx is called monic Chebyshev. So we have this equation, star, divide star by 2 to the n, let's say. Then see what happens. 2 to the minus n, Tn plus 1 equals x times 2 to the minus 1 minus n, Tn, minus 2 to the 2 to the 2 minus, we want this to be 2 minus n, right? Because that's, yeah. But because we have to take this, right? So this means Tn plus 1 hat equals x times Tn hat minus 2 to 1 over 4 Tn minus 1 hat if n is greater than or equal to 1, right? But if n equals 0, so T0, you just compute this separately. So this is the same thing as the Tn, so it's just x T0 or Wait, is that right? I think I made a mistake somewhere. Okay. What is t0 equals 1, t1 equals x, t2 equals 2x squared minus 1, I think. So, and t0 hat equals 1, t1 hat equals still x, t2 hat is the monic 1, so like this. So, yeah, so I think this should be greater than or equal to 2. And so, if this is 2, n equals 1, we get 1 minus 1 over 2 t0 hat, because it's 1 over 2. So that means now we have this formula, exactly the three-term recurrence that we have written, the form that we have written. So tn plus 1, x equals x minus bn, tn hat minus lambda n, tn minus 1 hat for n greater than or equal to 1, where b is always 0, lambda n is 1 over 4 or 1 over 2 if n equals 1, if n equals greater than or equal to 2. So you can find the recurrence, three-term recurrence like this. The recurrence coefficient can be computed like this. So even if the original recurrence is not monic, is for non-monic polynomials, you can make them monic, and then you can obtain recurrence like this. I was not very accurate about these indices, but it's a simple thing to fix. I might have done something wrong there, but you got the idea, okay? 네.
저기 n이 1이 포함 안 되는 게 앞에서는 tn이 햇으로 가면서 제로일 때만 따로 빼지 않습니까?
네.
근데 저희가 처음에 tn 가지고 이제 tn 플러스 1 플러스 tn 마이너스 1이 2x tn인 게 t0도 포함되어 있으니까 n이 1 이상으로 들어가지 않습니까?
여기서요?
예.
네.
그래서 넘어가면서는 t제로만 따로 봐야 되니까.
네.
그래서 n이 1인 경우를 제외하고서 따로 잡는 게 맞으십니까?
아, 여기서?
예.
그런 거 같네요. 지금
t제로는 계산이 따로 돼야 되니까.
네네네. Okay. Yeah, I think, so this is correct. And yeah, so I think I was confused because this is n plus 1, and so this is n, so I think that's where I got confused. But this is a simple thing, so you should be able to do this if you are doing this carefully, okay? So there's nothing seriously difficult here. So, any question? All right, so let's see what. Right, so Chebyshev polynomials, in the monic case, we have Bn equals 0, right? So in this case, the polynomials are a little special. So if the Bn equals 0, then the monic orthogonal polynomials P and let's say P2nx is an even polynomial or even polynomial, odd polynomial. Maybe let me just write a function that's more common, I think. Even function means, this means p2n x equals p2n minus x. This basically means even odd function basically means this. Oh, yeah. Like that. Okay, so even function means if you replace x by minus x, the function doesn't change. Odd function means if you change x by minus x, then you get minus sign. So, and this can be easily seen because if this disappears, then x always comes in pairs. Like here, you know, this is even, odd, even. But if you want to compute t3, then you multiply x here, so it'll be odd. And you get previous one, this is odd, so it's going to be odd. So even and odd alternates. So you always have even polynomials or odd polynomials if bn equals 0. Okay? This is, so actually in this case, it turns out that all the odd moments are 0. So let me first define this and prove a theorem related to this. So a linear functional L is called symmetric if all of its odd moments are 0. That means 2n plus 1, 0 always. And the theorem is okay. So we assume that this is linear functional with monic OPS Pnx. Then the following are equivalent. So first, L is symmetric. All the odd moments are 0. Second, Pn, even polynomials are even functions, odd polynomials are odd functions, like this. Yeah, this is basically what this means, right? And second, third, Bn equals 0 for all n in the three-term recurrence. These three are all equivalent.
두 번째 조건에서 하나는 마이너스 x가
네. Oh yeah, thank you. Yeah, I keep making typos here, but yeah, please correct me if I make typos here. Yeah. Okay. Yeah, I wrote in my lecture notes correctly, but I'm not really good at copying things. Anyway, proof. 1 implies 2. Symmetric, then this. If L is symmetric, implies that L of pi minus x equals L of pi x for all polynomials pi. Is that right? So the difference between these two are only appearing using odd moments. And odd moments are all 0, so they don't really contribute any difference. So they are the same. Okay, so therefore, we have Pm minus x, Pn minus x Doesn't really matter if you use minus x or x. So it's the same thing as pmx, pnx, right? But what is this? This is kn delta mn. Kn is non-zero. That means this sequence is also on OPS, right? That means Pn minus x OPS for L, right? But once you have a linear functional fixed, then OPS is unique up to scalar multiplication. So that means these two orthogonal polynomials must be scalar multiples of each other for some scalar, Cn. But now you know the Cn, what the Cn must be. Just look at the leading term. The leading term is minus 1 to the n. The leading term is Cn. They must be the same. So that's the. This is what this means. So this is done. And then 2, we're going to go in this direction. 2 implies 1. This then symmetric. Okay. Okay, since now let's consider P2n plus 1. Then this will be minus by the assumption P2n plus 1 x is odd function. Then okay, yeah, right. This means maybe I can write the next line to show. Odd polynomial means, odd function means we only have odd power of x in the polynomial. So this will be, it's a sum of odd moments with some scalar multiples, of course. And this is 0 if because this is always positive, so by orthogonality it will be 0. So sum of all the odd moments is 0, but actually this 2n plus 1 appears with coefficient 1 plus lower odd moments. We may have some multiple there, but this is okay. But by induction, so the first will be 0. First, mu1 will be 0, and then mu3 is 0 because of this. Mu5 is 0, so mu2n plus 1 is 0 for all n. So that means exactly the symmetry. This is done, and now we're going to prove 2 and 3, equivalence of 2 and 3. All right. To do this, let's define another function qn to be minus 1 to the n pn minus x. So 2 means pnx equals qnx, right? So in other words, to prove this, we need to show that this is equivalent to this. This is what we want to show. But we have a recurrence for, where is it? Yeah, let me copy the recurrence here. I think I can just move on. And because, just for the let's recall this. I think you can just remember this, right? Yeah, so we have a recurrence for this, Pn, but how can we get a recurrence for Qx? Okay, yeah, let me copy this. Yeah, it's easier if you can see right next to it. So because of this, here replace x by minus x and multiply minus 1 to the, say, n plus 1. And what happens? See what happens. Then minus 1 to the n plus 1, pn, minus x, right? Minus x minus bn, p, minus 1 to the n plus 1, pn minus x, minus lambda n, minus 1 to the n plus 1, p n minus 1, x minus x. But this is nothing but q n plus 1 x equals, you can cancel this one minus here with this, and x plus bn, qn. And this is, you can replace this by n minus 1, so it's lambda n qn minus 1. Okay? So now compare these two equations. When do they, when q is equal to p, if this is the only difference, the sign of this is the only difference between these two. They have the same initial conditions. So thus pnx equals qnx if and only if bn equals 0. Yeah, so one important theorem we proved today is that orthogonal polynomials always satisfy three-term recurrence relation. And in fact, its converse is also true. If you have a sequence of polynomials satisfying that three-term recurrence, then it's going to be a orthogonal polynomial sequence. That means there is a linear functional which makes this sequence an orthogonal polynomial sequence. It's a very famous theorem in classical orthogonal polynomial theory, and we will prove this next time. So, thank you.